In this lesson, we will learn another way to solve systems of linear equations. At the very least, by now you should be familiar with how to solve systems of linear equations using the graphing method. You may have also already studied the substitution method. In this lesson, we will talk about how to use linear combinations, also known as elimination. Let's consider this system of linear equations. We have 2x plus 3y equals 7, and 5x minus 3y equals 14. One of the biggest advantages of using the new method that we're about to learn is that it can be easily applied to equations that are in standard form. In order to solve either of these equations for either x or y, so that we could easily then use the substitution method, it would require a couple of steps, and that would generally be a lot more work than what this new method will be, because there's terms in both the variables with terms in it are on the same side, so we're going to have to move the term, we're going to have to then multiply both sides by a reciprocal of a coefficient. It's going to be a couple of steps. Generally, if you use this new method of linear combinations, you will save yourself a step or two. So let's consider how we're going to do this. Essentially, the steps for solving a system of equations using linear combinations is to first get one of the terms with the variables to be opposites in both equations. For instance, if we look at the x variables, we'll notice that the first equation has 2x and the second equation has 5x. Those are not opposites. If we go ahead and change subtraction to addition by adding the opposite, notice what happens in the y terms. The first equation has 3y, the second equation has negative 3y, and those are opposites. So that's the very first thing that you want to do when you solve systems using linear combination. Get one of the terms with the variables to be opposites in both equations. Once you have opposites, as we already do in this case, it's a matter of adding the two equations together, term by term. So we're going to first add the x's together. 2x plus 5x is 7x. And here's why we want to make sure that we have some opposites. Because 3y plus negative 3y is 0. So we could put in here a plus 0, but 7x plus 0 is just 7x. So now we continue. 7 plus 14 is 21. Notice what happened when we added those two equations together. We eliminated one of the variables. The only variable we now have left is x. This is going to allow us to solve this equation for x, and then we can use that x value to substitute into one of the original equations to find y. And now we continue solving this just as a regular equation. We want to get x by itself, so we're going to have to multiply both expressions by the reciprocal of the coefficient. That'll leave us with x equals, and 1/7 of 21 is 3. So we know that x equals 3. However, whenever we're solving a system of equations, there's always more than one variable. In this case, there are two variables, an x and a y. So we're not finished. Just because we found x, we also have to go back and find y. In order to find y, we're going to take this x value and substitute it into one of the original equations. It doesn't matter which one you substitute into, because when you substitute x into the first one, you're going to get the same thing that you will get when you substitute x into the second one. So let's go ahead and pick whichever one is looks easier to work with. The first one appears to have smaller numbers, whereas the second one has larger numbers and a negative sign in it. So the first one looks easier, so I'm just going to opt to use the first one. So once you've solved for one of your variables, the next thing you have to then do is find another variable. So next we have to find y. And I'm going to do that by copying this first equation down here, 2x plus 3y equals 7. And then substituting in the value that I know x to be. I know that x is 3, so I'm going to substitute into x 3. So this is going to be 2 times the x value, which is 3, plus 3y equals 7. Notice now that this equation has only one variable, the y, so I can now easily solve for that. Need to continue simplifying this expression. 2 times 3 is 6. And now I need to continue with the steps. The variable's already in one expression, so I can get rid of all terms without my variable in it by adding the opposite to both expressions. This will leave me with 3y equals 1. And now I multiply both expressions by the reciprocal of the coefficient, which will leave me with y equals 1 times 1/3 is 1/3. Now I can put my solutions together in my x and my y together in a solution, which will be an ordered pair that will satisfy both the first equation and the second equation. I discuss in the video on substitution the methods that we have of writing these. If you're interested in all the methods, you can check that video out, but for now I'm going to list them in a solution set. There is only one point that satisfies this system of equations. So there's only going to be one point inside the set brackets whose x-coordinate is 3 and whose y-coordinate is 1/3. Note that these are not two solutions. This is one solution to the system whose x-coordinate is 3 and y-coordinate is 1/3. So again, the strategy for solving systems of linear equations using linear combinations is to first make sure that you have variables whose terms are opposites of each other. If you don't have that, you need to get that, which we'll discuss how to do in a future video. Once you have opposites, then you simply add the two equations together term by term. That will eliminate one of the variables, allowing you to then solve for the other variable. Once you have one variable, plug into one of the original equations, that variable, in order to solve for the other, then you'll have your solution set.